Hello Year 11, at this point you need to calm yourself, get those laughs over and done with. Unfortunately I can't be here with you today, but I do want to go through some stuff and make sure that this lesson is as valid as any other lessons. High expectations as normal, and good luck. We're going to carry on with our topic today of specific heat capacity. Make sure the title is underlined, please, and write today's date in the top right hand corner and classwork top left. Before we go any further, make sure your pens are down, etc. And I'm just going to go through a quick recap of what is meant by this term specific heat capacity. Last lesson you did a practical which involved putting a heater inside an aluminium block. You recorded the temperature of it and the temperature rose, but we didn't necessarily go through exactly what is meant by specific heat capacity. I want you to imagine now being at home and you turn on your oven and you decide to put it on to 200 degrees. You've just made yourself a nice apple crumble, so here's some apple and there's some crumble. You leave it in the oven for, 20-25 minutes. And the assumption is that the apple crumble has, of course, got hotter and it's probably reached about the same temperature. So your apple crumble becomes the same temperature as the oven. You then get it out the oven, put your mitts on, get it out, put it on the worktop, get your spoon, put it in your bowl. You might add some cream. Some people like custard. I prefer ice cream. And then you take your mouthful and ow, that really, really hurts. But what hurts? So, press pause, have a discussion. What is it about the apple crumble that makes your mouth hurt? Now, it could be melt in the middle chocolate pudding. It could be a jam roly-poly. It could be a McDonald's apple pie. But either way, what do all these things have in common? And why does your mouth hurt? So, press pause. Okay, hopefully you've had a chance to have a bit of a discussion. Which bit of the apple crumble is the thing that's going to burn you? So let's just remind ourselves, we have a bowl. In there we have some apple, so I'll colour that bit green. And I'm not sure I've got a colour for crumble, so we'll go for yellow, a yellow crumble. How lovely. Right, if you then separate the two, let's just focus on the top bit, the crumble. When it comes out the oven, it's at 200 degrees. Focus on the apple. When it comes out the oven, it's at 200 degrees. But it's not the crumble that burns. It's the apple that burns. In a jam roly-poly, it's the jam that burns. In the McDonald's apple pie, it's not the casing, it's the inside apple that burns. Oh, melt in the middle chocolate pudding. Lovely. But it's not the sponge, it's the bit in the middle that burns. The reason is they all have a higher specific heat capacity. In other words, they store their heat inside them for longer. So when you get it out the oven, the crumble, because it's got a lower specific heat capacity, that will cool down faster. The crumble has got a higher specific heat capacity, so it stays hotter for longer. And that's why it's the thing like the apple or the melt in the middle chocolate that burns your mouth. It contains more water. And I know last week or last lesson we mentioned the idea that water has a high specific heat capacity. It takes longer to heat up, that's why we need to leave it in there for 25 minutes, but it also takes longer to cool down. So let's think about our equation for specific heat capacity. We're putting energy into our food, or last lesson, we put energy into our aluminium block or into our water. When we put energy in, we expect the temperature to go up. But how much it goes up depends on how much you've got, so how much liquid or how big a mass the block is, but also the specific heat capacity. Different objects have different specific heat capacities. They have different properties. So if we want to work out how much energy we need to put in to raise the temperature, this is our equation. Now it's slightly more complicated than previous ones because we've got 3 different unknowns on one side of the equation. But fear not, we're going to practice today to give rearranging the equation a little bit of a go. Shorthand, we quite like shorthand in physics. Energy is given capital E, mass is given little m, specific heat capacity, well you can write specific heat capacity, SHC, or in books it's just C for capacity, and change in temperature, we write triangle T, delta T, it's a Greek letter, and that means change in temperature. So energy equals mass times specific heat capacity times temperature change. So how much energy is needed to raise the temperature by 1 degree C is what specific heat capacity means. So the higher the specific heat capacity, the more energy is needed to raise the temperature of it. So if we're going to rearrange this, let's go for M equals. So if we're trying to find the mass, so focus on the mass and then what we need to get rid of. All of these are multiplied together. So the mass equals the energy divided by the specific heat capacity times the temperature change. If we want to find the specific heat capacity, we need to remove the mass and the delta T, the change in temperature, and we want to move it to the other side by dividing through. So C equals energy divided by mass times delta T. And then the final unknown that we might want to find is how much the temperature changes. So again, we get rid of the other things that are on the same side and move them across. So change in temperature is energy over mass times specific heat capacity. At this point, I would write these 4 equations down into your notebook. So if your teacher can press pause, now would be a good time to copy these down, so you're going to need them shortly. In front of you, you should have a sheet with some specific heat capacity questions on. I'm going to ask you, please, to have a go at questions 1, 2, and 3. I'm just going to go through, however, some pitfalls that you'll need to be aware of, and also just go through an example question 1A. So first of all, let's just go through what we know. So we're given the equation at the top, and at some point you'll need to rearrange that equation as we've just done on the previous slides, and hopefully are now written into your book. The specific heat capacity of water is 4,200. So for all of question 1, you'll need to refer to that. It does ask to give your answers in kilojoules. There are 1,000 joules in 1 kilojoule. So you might end up needing to divide through by 1,000. And for each of the questions, it asks for a change in temperature. So you need to look for the difference between the start and the end temperature. So let's just go through question 1A together. I suggest you write down all of the unknowns. You then put it into the equation and then of course find the answer. So we've got 3 kilograms of water, so I've written M equals 3 kg. And we see the temperature changes from 5 to 60, so that means it's changed by 55 degrees Celsius. And we know at the top that the specific heat capacity is 4,200 joules per kilogram per degree C. So that's a high specific heat capacity. So that's going to take a long time to heat up and a short time to cool down. We then need to put it into our equation, choose the right form. We're trying to find energy. So we're looking for E equals M times C times T, mass times specific capacity, times temperature change. Whack it into a calculator and you get 693,000, and then you divide through by 1,000 for the final step, so it can be turned into kilojoules, 693 kilojoules. So, can you please now have a go at B, C, D, E and F? And then once you're done or nearly done, move on to question 2 and question 3. Do that now, please. Hints and tips for going through question 2. Just be aware it's 500 grams. So for all of these, you'll need to convert it into kilograms. So 500 grams is 0.5 kilograms. And for the next one, be aware you're given a specific heat capacity. It has changed from what it was earlier, so it's 900. And you've also got kilojoules throughout both of them, so you need to make sure you multiply back into joules. So multiply by 1,000, you need to convert it. Just in case you get stuck, I'm now going to go through each of the questions I've asked you to do. So get hold of a purple pen if you have one to hand. Question 1b, well, the mass is 20. The specific heat capacity for all of them is 4,200. So the temperature change is 35 degrees Celsius. Find the difference. Specific heat capacity times the mass times the change in temperature, and we get an answer of 2.94 million joules, or when you divide it through by 1,000, 2940 kilojoules. For C, the mass is 7 kilograms. So I'm just taking out the key information. Specific capacity doesn't change. The temperature change is 81. It's the difference between 87 and 6. And again, you put it into the equation, mass times specific capacity times temperature change. You get a number in your calculator, divide through by 1,000, and then your answer is in kilojoules. So this is how much energy is needed to raise the temperature by 81 degrees. For question 1d, same principle as before. Find the mass, we know the specific heat capacity of water, find the temperature change. So for this example, in order to raise the temperature of water by 82 degrees Celsius, we need to put in 5,166 kilojoules. Question 1e, again, 500, a bit more kilograms this time, a bit more mass. Specific heat capacity, the temperature change is only 15 degrees this time, but we need to add 31,500 kilojoules of energy to raise the temperature by 15 degrees. Question 1f, the mass is 34 kilograms this time. We want to raise the temperature of water by 45 degrees Celsius, the difference between the two numbers, and that works out at 6,426 kilojoules of energy. For question 2, you do need to be able to rearrange, and this is why you need to have the equation written down before in its different format. And also, I mentioned earlier, remember that 500 grams, it does need to be turned into kilograms, so 0.5 kilograms. Like with the others, set out exactly what you know. Get into the habit of setting out the key things from the question. Make sure the equation that you're going to use is set out. So energy is 500, mass is half a kilogram, and we increase the temperature by 10 degrees. So 500 divided by 0.5 times 10. So the specific heat capacity of this substance is 100. So this one is a low specific heat capacity. It's going to heat up quick, and it will cool down very quick as well. It won't store its energy for very long. Question 2b, again, we've got the energy, but this time it's in kilojoules. So we need to multiply by 1,000. So that gives us 12,000 joules. The mass is 0.5 kilograms. Change in temperature, this time is a big one, 124. And we work it out by putting it into the equation, we have the energy on the top divided by the mass times the temperature change. Question 2c, again, same format. We need to use energy divided by mass times temperature change, put the numbers in, and you get 1,721. For D, the answer is 7,680, and for E, it's 18.2. But again, a few things to notice. Needed to multiply by 1,000 because you're given the value in kilojoules. For F, 11,848. For question 3, this time we've got aluminium, so about 900, which is similar to what the value you calculated the specific heat capacity to be. This time you're trying to find the change in temperature, so you're going to give it some energy, the kilogram, also the aluminium has got a particular mass, and we know that the specific heat capacity is 900. So the mass is 5 kilograms in this case, the specific heat capacity for aluminium is 900, and the energy we're supplying is 9,000 joules. So how much would you expect the aluminium to go up by? Well, we can work that out. We can have the energy divided by the mass, which is 5, multiplied by 900, which is our specific heat capacity for aluminium, 2 degrees. Question 3b, again we've still got aluminium, so we're still using 900. The mass is 3 kilograms this time, and we're adding 20,000 joules of energy, so you're given it in kilojoules, need to convert it. So it's 20,000 divided by 3 times 900, so this time the block of aluminium will raise by 7.4 degrees Celsius. And for part C, still aluminium, different mass, 3.4 kilograms, again convert to 120,000, and this one works out to be just under 37 degrees, 36.8. At this point, hopefully you have marked your work. I hope that you've made some progress today. There are other questions for you to have a go at if you get to this point. Very well done, and see you next lesson.